Welcome to a new unit. I'm so excited. Now we're going to be talking about reactions and two main types of reactions in this unit, precipitation and redox. First, we've got redox reactions. Let's get started. Okay, redox reactions are reactions in which one substance gains electrons and another loses electrons. Typically, these take the form of synthesis, decomposition, single displacement, and combustion reactions. And we're going to go through each of these types of reactions one at a time. Starting with synthesis, two or more substances combine to form a single substance, also called composition. A lot of times I'll say composition instead of synthesis, or combination. Not all synthesis reactions are redox, only those whose substances gain or lose electrons. That's the hallmark of being a redox reaction. So, for redox synthesis reactions, we have two general forms. Two elements combine to make a compound, or an element and compound combine to make a compound. What we have in common with these products is that there is only one product. Two things make one. So one type of synthesis reaction we have is a nonmetal with a metal making a compound. So we have iron and sulfur making iron sulfide, or a nonmetal and a nonmetal making a compound. So we have hydrogen and chlorine making hydrogen chloride. Hopefully you've noticed that all of these compounds have in common that there is only one product, and hopefully you've also noticed that they also all have in common that they're not balanced. So let's balance those reactions right now. Starting with iron and sulfur, there's one iron and one sulfur on the left, but there are two irons and three sulfurs on the right. So the simple balancing just puts a 2 here and a 3 there. For sodium and chlorine, there's one sodium on the left and one sodium on the right, two chlorines on the left and one chlorine on the right. So we're going to fix that by putting a 2 in front of NaCl, which then messes up the Na, so a 2 in front of the Na. For the nonmetal and nonmetal, we have two hydrogens and two chlorines because those are diatomic molecules. So we need two hydrogens and two chlorines. And then we have one carbon and two oxygens on the left, one carbon and two oxygens on the right. That one is balanced on its own. We have decomposition reactions. Decomposition reactions are the reverse of synthesis, which is why a lot of times I call synthesis composition, because this is decomposition. A complex compound breaks down into two or more substances. Electricity or heat are generally required to decompose a compound. Not all decomposition reactions are redox, only those whose substances gain or lose electrons. So what the general form has in common with decomposition reactions is that there is only one reactant. That one reactant, one compound, can be split into two separate elements or an element and a compound. So that's a decomposition reaction. So we've got the first type is a metallic chlorate, like potassium chlorate. Will turn into a metallic chloride and oxygen. Let's balance that. 3 oxygens on the left and 2 on the right. Means I'll need to balance it with a 3 and 2. That gives me 2 Ks and 2 Cls, so I'll put a 2 in front of the K and the Cl. The other we have is magnesium chlorate, which turns into magnesium chloride and oxygen. So magnesium chlorate, that's got 6 oxygens there total, so I'll put a 3 in front of the O2 to give me 6 oxygens total. This has 2 chlorines because there's 2 chlorates, which I already have 2 of, 1 magnesium, so we're good. Another type of decomposition reaction includes an oxide breaking down into an element plus oxygen. So, for example, mercury oxide turns into mercury plus oxygen. There's 2 oxygens on the right, so I'll fix that by making 2 mercury oxides and then 2 mercuries. With Ag2O, that silver oxide makes silver plus oxygen. 2 oxygens on the right, 1 on the left, put a 2 there. That gives me 4 silvers. And then another type has hydrides, that's sodium hydride, turns into an element and hydrogen. And in this case we have 2 hydrogens on the right, because hydrogen is diatomic, so 2 NAs and 2 NAs. Third type of redox reaction is a combustion reaction, in which a compound reacts or burns with oxygen. Specifically, anything plus oxygen is a combustion reaction. So a general form can be an element with oxygen, we'll make an oxide, or a hydrocarbon with oxygen, we'll make carbon dioxide and water. This is the combustion reaction you are probably most familiar with, but it's not the only type. So if you have a metal and oxygen, such as sodium and oxygen, you'll get a metal oxide, no surprise there. So to balance that, I'll need 2 of those oxygens on the right, which gives me 4 sodiums. You could also have a nonmetal plus oxygen, making a nonmetal oxide. So carbon plus oxygen makes CO2. This is also a synthesis reaction because those two things are synthesizing. Actually, both of these are synthesis reactions, but they're considered combustion because they react with oxygen. A third type of combustion reaction, the one you're most familiar with, is the hydrocarbon plus oxygen. The products here are always CO2 and water every single time, no matter what. So just memorize those products. The trick with this type of combustion reaction is balancing it, making sure you get it all balanced. So let's start with the hydrogens, then the carbons, then the oxygens. The order you want to do it in is hydrogen first, then carbon, then oxygen last. So I got 4 hydrogens and 2 hydrogens. I'm going to fix that by putting a 2 in front of the H2O. I got 1 carbon and 1 carbon, so that's good. For my oxygens, I have 2 on the left, and 2 plus 2 is 4 on the right, so I'll fix that by putting a 2 on the right. For the next, technically CH3OH is not a hydrocarbon because it also has oxygen in it, but it's listed in this class because the products are CO2 and water, always CO2 and water. Still, we're going to balance it with hydrogen first. I've got 3 hydrogens plus 1 is 4 on the left and 2 on the right, so I'll put a 2 in front of the water. Then carbons, 1 carbon on the left, 1 carbon on the right, we're good. Then oxygens, I've got 2 plus 2 is 4, and then 2 plus 1 is 3. So that seems like that's going to give me a hard time. Let's erase what we have and think of a way to come back at this. So if I know I'm going to end up having 2 plus 2, which is 4 oxygens, let's see if we can fix those oxygens to start with. Let's put a 2 in front of the CH3OH, and then balance from there. This gives me 2 times 3 hydrogens, which is 6, plus a 2 times 1 hydrogen, which is 7, 8 total on the left, so I'll make 8 total on the right. Now carbons, I did 2 times C, so I'll put 2 times C. And now oxygens, let's try this again. I have 4 with the CO2, plus another 4 with the water, is 8 total on the right-hand side. Now I have 2 with the CH3OH, plus another 2 with the oxygen, is 4 total on the left. So if I had 8 on the right and 2 plus some number on the left, if I could make this 6, then that would be 8. So if I put a 3 here in front of that O2, then that's going to be 8. The reason why you want to balance oxygens last in the combustion reactions is because oxygen is usually a reactant on its own and easier to manipulate how many of them you have, whereas carbon and hydrogen are within other compounds. And the next one we're going to talk about is single displacement reactions. In this type of reaction, a metal will replace a less active metal in a compound, or a nonmetal will replace a less active nonmetal in a compound. The activity series must be used to determine if this type of reaction will occur, and we'll talk about the activity series in just a second. If a metal is higher on the activity series than the element it is attempting to replace, it is able to do so. If it's higher, it is able to do so. So I'm going to talk about the 3 general forms first, and then we're going to look at the activity series and see how that applies. So the 3 general forms would be a metal and a compound will make a new compound and a different metal, or a nonmetal in a compound will make a new compound and a different nonmetal, or a metal and water will make a base and hydrogen. This one's a little bit different because water doesn't have a metal in it, but it's still counted as a single displacement reaction. This will only occur if the metal is able to displace water or steam if it specifically mentions H2O gas according to the activity series. So again, we're going to be looking at this activity series. Here's what the activity series looks like. There are 2 of them, one for the metals, the big giant one on the right, which is on the left-hand side of your notes, and the other for the nonmetals, the little baby one that's on the left, which is on the right-hand side of your notes. So we'll start with the metal and nonmetal. These are the 2 examples from the metal plus compound makes a different compound plus a different metal. We're specifically looking at copper and silver, and whether or not that copper and silver will switch places. So what we need to do is find copper and silver on the activity series. And you see there they are, copper and silver. Since copper is higher than silver, copper will be able to replace silver. Since silver is lower than copper, silver will not be able to replace copper. Copper is going to switch places with silver because copper is more reactive than silver. Silver will then go sit alone. So copper becomes part of copper nitrate, silver sits alone. But the opposite reaction cannot occur. Since silver is lower, silver cannot switch places with copper. There will be no reaction. So for that top reaction, let's get that balanced. CuNO32, I'll need 2 nitrates on the left, which gives me 2 silvers. Okay, so for the next part, this is using the non-metal activity series. Here we've got sodium bromide and chlorine. The reason why I'm using the non-metal activity series is because there are 2 nonmetals on the reactant side, not 2 metals on the reactant side. And what we're hoping to happen is bromine and chlorine are going to switch places. So you need to find bromine and chlorine on the non-metal activity series. And notice that the non-metal activity series is actually just the list of halogens the way it is on the periodic table. Fluorine is higher than chlorine, which is higher than bromine, which is higher than iodine. All 4 halogens in order. Chlorine is higher than bromine. Chlorine will be able to replace bromine. So this reaction occurs and we get sodium chloride plus bromine. But if you look at the next one, we have fluorine and bromine. And check it out, fluorine is higher than bromine, so fluorine can totally replace bromine, but bromine can't kick out fluorine. This reaction is not going to happen. There is no reaction. So then let's get that balanced, 2 and 2. So then the last type we have is a metal plus water makes a base plus hydrogen. And in this case, we're assuming the hydrogen from the water is like the metal that it's trying to replace. So what we're trying to get to happen is sodium to go replace hydrogen and hydrogen to sit alone. So in this case, we need the displace hydrogen part of the activity series. Notice that all of these metals will displace hydrogen from acids. These metals will displace hydrogen from steam, and these are the only 4 that will displace hydrogen from water. So it specifically has to say that it is water. And I notice that sodium is missing off your list, which is awful. Let's put sodium right up here at the top. Sodium should be up there with displaced hydrogen from water because this reaction does happen. So, in this case, since sodium's supposed to be up there at the top, sodium will provide a reaction and replace hydrogen. And so we get sodium hydroxide and hydrogen. Let's get that balanced really fast. There are 2 hydrogens, 2 OHs, 2 sodiums. So for the next one, we have lithium and hydrogen. And we're trying to get lithium to replace hydrogen. And notice lithium's also up here and displace hydrogen from water, so this will totally happen. We'll get lithium hydroxide and hydrogen, and that balances the same way. So you can kind of think of single displacement reactions as a couple working together and a single person coming along beside them, and the single person is trying to break up the couple. Can the single person break up the couple? It just depends on whether or not the single person is more attractive, or in this case, active, and is higher on the list. If the single one is more attractive or more active, the single will replace something from the compound. If the single one is less attractive or less active by being lower on the list, the single one will not replace someone from the compound. Okay, well that's all we have right now for the activity series. I hope to see you again next time.